Hey guys, we're going to talk about horizontal projectiles today. So in this picture, we've got a plane that has a package and it's dropped the package. So we see the trajectory of the package as it falls. Notice that it's parabolic. That's important. So we've got that parabolic curve just like with angular projectiles. We also want to pay attention to the idea that the object was launched horizontally and is freely falling. So that means we're going to follow our free fall characteristics, first of all. And second of all, we know that this was launched straight out horizontally and there was no kind of angle of any sort at the beginning. Okay? So in your notes, you've got some questions that ask, first of all, what's happening to Vx? So notice Vx here is this one. Okay? Vx is the same the whole way through, okay? Why doesn't it change? Well, there's no air resistance in a free fall, right? And so if there's no air resistance, there's nothing to change Vx, all right? So it's going to maintain its 115 meters per second the whole time. And that's because that's how fast the plane is going. Okay, it's important to notice that our object has stayed right below the plane the whole time. And again, we've got no air resistance, no wind, no drag, so there's nothing to affect that sideways, that horizontal speed that the package got from the plane. Okay, our next question is what's happening to Vy? So if you take a look at Vy, we see that there is no Vy up at the beginning, right? And then we move to a kind of a short arrow, and then we've got a longer arrow at the end. So Vy is definitely increasing, right? We see it increase as the plane goes. And why is Vy doing that? Well, gravity is acting, right? So it's going to speed up this package as it falls. So then the question, is the object accelerating? Definitely, right? And it's accelerating because of the force of gravity. That force of gravity is causing that package to speed up but at a rate of negative 9.8 meters per second every second. Okay. Our next question is what is V? What does V represent? Okay, so let's look at V. V is this one here. And notice that it is increasing as it goes as well. And notice it's at the angle. If we were to move our Vy over so it was head to tail with Vx, we would see that we have a nice little triangle here. And so this tells us that our V is the resultant. Okay, it's a resultant or combined velocity. Just like it has been in our angular projectiles that we've been working on. Same idea here that V combines Vx and Vy. Okay. Next question is what would happen if the plane was traveling faster? So let's say that instead of 115 meters per second, we're going to go 215 meters per second. So our plane flies faster to begin with. When it drops the package maintains that same speed. Okay. Now it's not changed location, the plane hasn't, and so it's not going to be in the air any longer. However, it is going to land further away because it's going faster, right? So it can cover more horizontal distance in the same amount of time. Okay, so if plane is faster, then we will see an increase in delta x. And that's really all that we see change. Time does not change, Vy does not change, it's just a delta x, and it's because it can go further in the same amount of time. Our last question is what would happen if the plane would drop from higher up? So let's say that our plane is way up here, new delta y, okay. If the package drops from further up, then several things are going to happen. So we have a greater delta y. Because we have a greater delta y, then that means gravity acts for a longer time. So Vy will increase. Okay. We also will see time increase because we're starting from higher up. Okay. And then last but not least, because it's in the air for longer, delta x is going to increase too. Now it's going to increase not because anything happened to Vx. We're still moving at 115 meters per second, but it's in the air a longer time, so it's traveling at that speed sideways for more time. And so again, we're going to land further away. Okay, so changing height changes quite a few variables. Changing Vx just really focuses on one thing. Okay, so if we take that knowledge and ask ourselves a very classic physics question, which is if a bullet is fired from a gun horizontally and a bullet is dropped from the same height at the same time, the gun is fired, which bullet hits the ground first? Well, we can answer that based on our physics. Okay, so you can see here from my screen that they hit at the same time. If you need a visual, you've got one bullet that is launched out really, really quickly, right? But gravity is going to start affecting it as soon as it's out of the gun, and so it is going to fall at that parabolic trajectory. Our second bullet is not launched, it's just dropped straight down. But it is really important to note that these are happening at the same height. Okay, so what do we know that height affects? Height affects time. So they're in the air the same amount of time. We know that that means gravity has the same amount of time to affect them. And so because of that, we see that they fall from the same height with the same acceleration. They will hit at the same time. Remember, the horizontal and vertical motions don't affect each other. They're independent, right? And so that means that although this first bullet has a Vx and this one doesn't, that only affects where the bullet lands and not how long it's in the air. There is actually a Mythbusters show where they tried this, because I know sometimes it's a little bit hard to believe. We watched it in class, but if you weren't able to be there with us, you might look it up on YouTube and see if you can find it. They shoot a bullet and they drop a bullet, and they do see that the physics textbooks are correct and they do hit at the same time, even in real life. Okay, so from there, let's go ahead and try to work some examples. Pictures are not required on these examples, but they are really helpful in breaking down our variables. So let's just start with a picture here. We've got a stone. It's going to be kicked off a cliff. Notice that our trajectory is parabolic. It is not a triangle. Okay, they tell us that the cliff is 44 meters high, and they tell us that our stone is kicked off at 15 meters per second. Okay, so first thing we want to do, just like with angular projectiles, is to set ourselves up with an XYT chart so we can break down our variables and figure out what we have and what we need. The 15 meters per second is a Vx because this was launched horizontally. The 44 meters is a delta y because it's the height. We also know that Vyi is going to be 0 because this acts like a free fall object. When it's kicked straight out, there's no downward force before gravity starts affecting it. And so Vyi will always be 0 on horizontally launched objects. And then acceleration is caused by gravity, so that is only on our y side. Always only on the y side. Okay, so when we're thinking about our equations, we've got the one horizontal equation, and then we've got 3 vertical equations to choose from. We don't have enough information on our x side, so we've got to look at the vertical, right? And we see that we don't know and do not care about final vertical velocity, or VYF, so we're going to choose the equation that doesn't have that in it. Okay, so that's nice because it narrows it down to the delta y equals Vyit plus 1/2 at squared. Okay, now Vyi is 0, so I'm just going to get rid of that whole first part, and then I'm going to plug in my numbers. Our stone is falling 44 meters, so I'm going to put negative for delta y, and then I have 1/2 times negative 9.8 times t squared. Okay, so first thing to do is to multiply 1/2 times negative 9.8, so now I have negative 4.9 times t squared. My next step is to divide both sides by negative 4.9 as I work to get t squared by itself. And so that gives me an answer of 8.97 with lots of decimals equals t squared. But I don't want t squared, I just want t. So I'm going to take the square root of that, and I get a delta t of 2.996, lots of decimals, so I'm going to round that to 3.0 seconds. Okay, so there's my answer for time to the bottom of the cliff. I don't have to worry about half time or whole time because I'm basically starting at the peak. So the half time is the whole time. So don't worry about that part from angular. Okay, our second question is how far from the base of the cliff does the stone fall? So I'm looking for this, right? That's going to be delta x. Okay, so I know that I have Vx, and then I just solved for time, and it was 3.0 seconds. And so I can use my one horizontal option, which was delta x equals Vx times t. I fill in my numbers. I had 15 meters per second for Vx. And then I have my time of approximately 3 seconds. Now I actually am going to use my 2.996 lots of decimal seconds because I haven't taken it out of my calculator yet, and this will give me a more precise answer. And that gives me 44.95 meters. Now I've drawn my picture with that to the right so I can add a plus. That part is a little bit ambiguous on these problems, and so don't worry too much about direction and worry more about figuring out the algebra. All right, one more example. Let's try this. So in this one, we have a student who throws a baseball horizontally out of a window 8 meters above the ground. Okay, another student catches the ball 10 meters away. So I've got 10 meters down here. I have 8 meters up here. Clearly my picture is not drawn to scale. Notice again that this is a parabolic. It's a curve. It is not a straight line. You cannot make this into a triangle because the ball does not follow a triangular path in real life, right? We can't do this and make a nice neat triangle because no ball is actually going to do that. Okay, so knowing that we have now set this up correctly, we're going to do our t-chart. Okay, so we're splitting horizontal and vertical variables. We know that our student catches the ball 10 meters away, so that's delta x. We know that the first student started 8 meters above the ground, so that's delta y. We know that this follows free fall rules, so Vyi is 0 and a is negative 9.8, and that of course only goes on the y side. Okay, what was the initial velocity of the ball is the question. So if our student throws this out horizontally here, we know that that means we're looking for Vx. Okay, so take a look at our column. Do we have enough information in the x column to solve for this? We don't, right? We need two numbers. So our step one is going to be to solve for time first. And we're going to use the y side to do that. Okay, because we do have enough information to use our delta y equals Vyi plus 1/2 at squared formula. This is the one we're going to choose because we do not know final velocity and we don't care about final vertical velocity. Okay, so as usual, Vyi is 0, so I'm going to cross that out. So I have negative 8 meters equals 1/2 times negative 9.8 meters per second squared times t squared. Okay, so my first step, of course, is to do 1/2 times negative 9.8, and then that is times t squared, and then I'm going to divide both sides by negative 4.9 to get t squared by itself. So t squared is approximately 1.632, lots of decimals. I'm going to take the square root of that though because I want t and not t squared. And so I have a time of 1.2777, etc. Okay, I'm going to go ahead and just leave that with a lot of decimals for now. So now my step 2 is going to be to solve for what I'm actually needing to solve for, okay, which is to find Vx. That's what the question asks for. So I'm going to use my horizontal equation, which says Vx equals delta x over delta t. I'm going to plug in my numbers from my chart. So I have 10 meters over 1.2777, etc. And when I put that into my calculator, I get about 7.83 meters per second. And that is my final answer for this problem.